Okay, so today, all we have left to do is finish up lecture set number 12. And that brings us to the conclusion of the materials for the class. Now, last class we left off talking about or learning how to compute and interpret the coefficient of determination. So at this point, we actually had everything we needed to complete assignment 6. So assignment 6 ends here, okay, and it covers lecture sets 11, and then obviously up to this point in lecture set 12. Okay. All right. So the point being, like, of course, that you can finish assignment 6 at the end of last class. I came into my office this morning and there was an envelope on my desk with my name, and I opened it and there's a USB stick inside, and I have no idea like what it is. I'm like, I'm not putting this into my computer. And I just looked at it again. I'm like, where is this thing from? And actually, I think I'm starting to remember what it is, but it weirded me out for some reason. Just like put it in the computer and everything just turns off and the university shuts down. It's like, oh God, why did I do that? It is a little sketchy, but it had my office. No, you're right. And it looks like I don't recognize the writing on it either. Like, it's not like nice printed writing. At least like a letter, like, hey, this thing would be good. I should probably try and shred it in the paper shredder. Yeah, but it could be a terrible movie too. The main character in what? It's probably really not anything interesting. I'll probably like put it in and it's just like a parking ticket or something. Anyways, I digress. Okay, so the last two major things that we're gonna talk about in this lecture set are I don't know if I'm ever gonna look at it. Yeah. Let's just talk about ideas for what this could be for the rest of today's class. Okay, so the last two things that we're going to talk about in this lecture set are a hypothesis test and a confidence interval. Yeah, more. Those topics are not tested on the assignments and obviously won't be tested on the lab quiz, but they will appear on the final exam. So this material is still testable, and there will be a question devoted to each on the final. So you still need to know it. But that's the only place that you'll see it in terms of actually being tested in the class. So we're going to go through that. It's not going to take us an hour and a half. Once we get through it, I'm going to show you guys one of I call it like it's like a flow chart of all the different hypothesis tests we've seen in the course. So I'm going to review that with you, and then I'm going to post that on Blackboard. And then following that, we'll talk about assignment 6. So I'll take questions on assignment 6. And then we'll finish off there. And on Tuesday next week, we'll do review. Okay, is the final open book? Yeah, of course. It has to be open book. Okay, so we introduced linear regression analysis. We introduced the ideal or the types of situations in which you would want to use regression analysis. So we have paired data, but we're measuring two different variables, and we want to try and predict the value of one variable from the other. So in the example that we've been using throughout this lecture set, we're trying to predict a student's midterm score based off of how much they slept the night before the exam. And what we've observed is that the more you sleep, the higher your midterm score tends to be. So this obviously is, a curated example, if you will. We talked about how to fit the line. So we're going to use the equations for B1 and B0. We talked about how to interpret the values of B1 and B0. And then what we finished off talking about is how can we evaluate the fit of the line? So this can be done through the R or the R squared value. And those two values are actually very closely related because R squared is just the square of R, or R is the square root of R squared. We also gave a set of sort of standards by which you can interpret R. So you can use these to figure out kind of like how strong the relationship is. It's kind of a rough guideline of the strength of the relationship. And and we talked about the interpretation of R squared. Okay, so to set up the inferential part of this lecture set, so the hypothesis test and the confidence interval for a regression model. Just like any inferential procedure, there's a set of assumptions in which we would base our inferential procedure on. The first assumption, which is labeled population regression line, this assumption basically is stating that we can assume there is a linear relationship between the population response and the population predictor variable. So if you think of our data set as being a sample from the larger population of first-year biology students, we are making an assumption that there actually is a linear relationship between midterm mark and the number of hours that you sleep. And we can evaluate this assumption simply by studying our scatter plot. So if our scatter plot of the sample appears to be linear, this would give us evidence that there is a linear relationship between the response and the predictor. So we've actually seen examples of this already. And I kind of hinted at this being necessary because you're not going to want to fit a straight line to something that isn't linear, because that would be a poor predictor of that relationship because it's not actually capturing the relationship at all. The fourth assumption is another classical assumption. So the fourth assumption is that we have independent observations. So basically, for example, in our example, we have 15 students. We're making the assumption that those 15 students are independent of one another. Okay. So they don't influence each other's grades. So we're, no cheating, that kind of thing. The next two assumptions are that every single observation in the data set actually is normally distributed, and every single observation has a normal distribution that has an equal standard deviation or an equal variance. Those two assumptions are trickier to evaluate. Sort of like with the ANOVA situation, we have to use residual analysis to evaluate those assumptions. But this is beyond the scope of the course, so we're not going to go into a lot of detail on how to actually do this. But the idea is not so far removed from what we have seen throughout the other tests that we have talked about in the class. So normality of the response variable or normality of the variable of interest has been a constant assumption throughout the course, and it remains a key assumption for linear regression. All right. So I've talked about residual analysis a couple of times. I've kind of mentioned that this is a technique that we utilize to test the assumptions of our models, specifically in the case of ANOVA and linear regression. And what's interesting is that ANOVA actually is a special case of linear regression where the predictor is not constant. And we talk about this in a lot more detail in Stat 252, and we get into residual analysis in much more detail in Stat 252 as well. So for now, the point is just to kind of touch on these ideas so that you have a bit of an understanding of some of the places that we're going to go at the next level. In terms of what residual analysis actually is, the starting point is the definition of the residual. So a residual is simply a measurement of error. And it's the difference between the actual observed value of y and the predicted value of y using the regression model. So little ei is the difference between what we actually have in our data set and what we would predict to have from the model that we fitted. So for the midterm mark versus sleep data, an example of the residuals are shown here. So here is our original data set. So this is X, this is Y. Okay, so these are the observed quantities. Okay. And this here are the predicted mark for every single value of X that we have in our data set. So you'll recall that Y hat is equal to 39.221 plus 5.902 times X. So each of the predicted marks here are found by plugging X into our linear model. So for example, this last quantity here, 52.25, this is 39.221 plus 5.902 multiplied by 2.2. And every single value in the predicted column follows the same, or is calculated in the same way. You take your regression line and you sub in the number of hours of sleep for X. Okay, so like as a second example, this quantity here is 66.37 is equal to 39.221 plus 5.902 times 4.6. Okay, the residual is then the observed value minus the predicted value, right? So 1.63, this is 68 minus 66.37. Negative 6.39, this is 83 minus 89.39. Negative 7.11 is 51 minus 58.11, etc. So the residual is actually just the difference between the line and the point. So if you think back to the scatter plot that we have of our data set with the superimposed line, okay, so that was on slide 10. Okay. Go to slide 10 for visual representation. Okay, so if you head back to slide 10, basically the difference between the point and the line, this is the residual. So every single observation has a residual. Okay. So this would be true for all values in the data set. They all every value contributes a residual, and the residual is just the space between the point and the line at that value of X. And again, that's true for every observation. Okay, any questions so far? All right, so we have to understand what the residual is for testing the assumptions of the model, but we also need the residual in order to conduct inference about the model. So we define it so that because we're going to use it a little bit later. All right, for the most part, when you see the hypothesis tests and the confidence interval for the regression model, you're going to be able to assume the assumptions are intact because, again, we're not going to study assumption validation at this level. So assuming that we have the assumptions intact, the hypothesis test that we are going to study is called the test of no linear relationship, or it's called the model utility test. So it has a couple of different names. This test is a two-sided test of beta 1 equal to 0 versus beta 1 not equal to 0. This hypothesis test is actually a very useful test because what it is doing is it's testing whether or not the response and the predictor actually form a linear relationship. So you can imagine that if our regression line is equal to, if our regression line is y equals beta 0 plus beta 1x, if beta 1 equals 0, y equals beta 0. So if beta 1 is 0, this means that x plays no role in predicting y. So it means basically that y and x are independent of one another. So this test is basically using the data to determine if x is actually useful in predicting y. So it's a very helpful test in that it's actually giving us a very meaningful conclusion about the relationship that we are studying. Okay, any questions about that? Okay. Okay, so this hypothesis test, as I mentioned before, is a two-sided test, and it always is going to be beta 1 equals 0 versus beta 1 not equal to 0. You can conduct other types of regression tests, but this is the test that we're going to focus on in this class. So the two-sided test about beta 1 being equal to 0. And this is called the test of no linear relationship, or the model utility test. In order to conduct this test, we're going to use a hypothesis testing procedure. So we have our 6 steps. On step 3, we compute the test statistic. For beta 1, we can show that the test statistic is a student t random variable. So the regression test is conducted using a t distribution, and the t distribution has n-2 degrees of freedom in this case. Okay, so we've seen lots of examples of t-tests in the course. This is the exact same procedure. The only difference is the formula for the test statistic and the degrees of freedom for said test statistic. In our test statistic calculation, we have a term called little se. Little se is the square root of SSE over n-2, which is actually the square root of the sum from I equals 1 to n of the residual squared over n-2. So you can see that little se is the sum of the squared residual. So it's basically a measure of the squared difference between the point and the line. Okay, so this is where we can use the residual term within the context of the test. Sorry. All right. Okay, so the formal steps of our test of no linear relationship are given on slide 26. So for the test of no linear relationship, we're always conducting a two-sided test of beta 1 being equal to 0. Step 2 is a significance level. Step 3, test statistic. So because of the form of the test, this will always be b1 minus 0 over SE divided by the square root of SXX. Step 4, critical value or p-value. It's a t-test, so we're going to use the student's t-table. Step 5, decision. Step 6, conclusion. So it's our typical 6-step process, and this depends on the 4 assumptions that we had talked about for the regression model. But again, for the purposes of this course, we're interested in working through and interpreting the test. You are going to be able to assume that the assumptions are intact when you see this test on the final exam. Okay, we can also build a confidence interval about B1. This is going to be done in a fairly natural way given the definition of the hypothesis test. So Step 1, find your t value. Step 2, build the interval. The form is shown on slide 27. Step 3, interpret the interval, and this would be done in the usual way. Okay, so for our midterm mark versus sleep data, we're gonna demonstrate, or I'm going to demonstrate the regression t-test and the regression and the construction of the confidence interval. Okay, first off, in both situations, we're not given a significance level, so we're going to assume alpha equals 0.05. That's the standard. So if you're not explicitly given the value, you can assume alpha is 0.05. All right, so we'll start off by writing assume all assumptions are intact. Okay, so we're performing a regression t-test. So on step 1, we have beta 1 equals 0 versus HA beta 1 not equal to 0. Step 2, we have alpha equals 0.05. Step 3, we have t is equal to b1 minus 0 divided by little se over the square root of sxx. So this is going to be 5.902 minus 0 divided by 6.710038 over the square root of 77.544. Okay, and this is going to be a number. $7.745. Okay. So then on step 4, we can take the critical value approach or the p-value approach. This is a two-sided test. Okay. So that means that we're going to have t alpha over 2 n minus 2 and negative t alpha over 2 n minus 2. Okay. So this is going to be t 0.025 comma 13. So we're going to use our t table now. Okay, so we have 0.025, 13 degrees of freedom. So that gives us a critical value of 2.160. Okay. So here we have 2.160, and here we have negative 2.160. This is our rejection region. And you can see that the t value is embedded within the rejection region, so we can reject H naught. Okay, if we take the p-value approach, okay, so we're going to have t equals 7.754 and negative t equals negative 7.754. So here we have our p-value. Yeah, so the same as with the assignments, it'll specify when to use which approach. So if it tells you to use the p-value approach, you have to use the p-value approach. If it tells you to use the critical value approach, you have to use the critical value approach. If it doesn't specify which approach, you can choose. So that will remain the same as it was handled with the assignments. All right. So here, the p-value is going to be equal to 2 times the probability that t exceeds 7.754. Okay. So then we can say, since the probability that t exceeds 7.754, so now we go back to our t table. Okay, we have 13 degrees of freedom. As we scroll across the line, we can see that 7.754 is greater than the largest listed value, which is 3.012. Okay, so that means that the probability that t is greater than 7.754 must be less than 0.005, right? So our value is greater than the biggest listed value. So the area to the right of the positive must be less than 0.005. So since this is less than 0.005, then the p-value is less than 0.01. All right. So hopefully all of that looks very familiar to you at this point. Does anyone have any questions? Two times 0.005. Any other questions? Okay, so given the critical value or the p-value approach, we can reject H0. So the critical value approach is showing us that the test statistic is in the rejection region, so we can reject H0. And the p-value is less than 0.01, which is smaller than 0.05. So therefore, we can reject H0. Okay, now the interesting part. So for our conclusion, we can start off with at the 5% significance level, the data provide sufficient evidence to suggest. Okay, so the starting point here is the same as all of our other conclusions. We have our significance level, and now we're rejecting, so the data are providing evidence. There's a couple of different ways that we can phrase this. The easiest way to phrase the question is to say, or phrase the conclusion, is to basically say the data provide evidence that the true population slope does not equal 0. But that's kind of a boring conclusion, because what this test is really telling us is that there is evidence that midterm mark and the number of hours of sleep form a linear relationship. So since we found evidence that beta 1 does not equal 0, this is telling us that y is actually a function of x. So it means that y equals beta 0 plus beta 1x. Therefore, the test is actually telling us that there is a linear relationship between x and y, which is why we call it a test of no linear relationship. So we can write, since we rejected H0, at the 5% significance level, the data provides sufficient evidence to suggest that the number of hours of sleep and midterm mark are, or let's be a little more, form a linear relationship. Okay. Any questions? Okay. In part B, we're asked to construct the regression interval. So basically what we're doing here is we're going to build a 95% confidence interval for beta 1. Again, there's no significance level or confidence level stated, so we're just going to assume alpha 0.05 because that's the standard. So in step 1, we're going to compute our t value. So we have t alpha over 2 n minus 2 is t 0.02513. So this is the same value that we used for the hypothesis test. So now what we should start to think is, okay, if we're using the same critical value for the test and the interval, these conclusions are likely going to agree with one another. Okay, step 2. So we're going to have B1 plus or minus T 0.02513 multiplied by little se over the square root of sxx. So this is going to be 5.902 plus or minus 2.160 multiplied by 6.710038 over the square root of 77.544. So that's 5.902 plus or minus 1.645. 1.646. All right, so that gives us 4.256 to 7.548. All right, so now we can say we are 95% confident that the population slope or the population value of beta 1 is between 4.256 and 7.548. But again, we can recognize here that the slope is telling us how much the response variable changes for each unit increase in the predictor. So what we have actually found here is we are 95% confident that each additional hour of sleep will lead to a increase of between 4.256 and 7.548% on the midterm. Okay, so what this interval is giving us is a range of how much we expect the response variable to change for each unit increase of X. So for each additional hour we sleep, so for each extra hour that we get, this interval is telling us that our mark on the midterm should increase between 4.256 and 7.548%. Any questions? Like, do you mean like, is what I wrote enough information to be giving full marks? Yeah. Yeah. Okay, so the last thing I mentioned before that we're using the same critical, yeah, that's what I'm going to talk about now. So I mentioned before that the hypothesis test and the interval should agree. So the hypothesis test showed that beta 1 does not equal 0. Okay, so in the hypothesis test, we rejected the null hypothesis in favor of the alternative. The alternative was that beta 1 does not equal 0. The CI does not contain 0, right? So the confidence interval is telling us that beta 1 is between 4.256 and 7.548, which does not include 0. Therefore, the interval and the test are giving us the same conclusion, that beta 1 is different from 0. So that's how they agree. They're giving the same result in terms of beta 1 being different from 0. Had we not rejected the null, so suppose that we did not find evidence that beta 1 was different from 0, then the interval would include 0. Does that make sense? Any questions? Okay, so lecture set 12 is devoted to simple linear regression. So the study of the regression line between y and a single value of x. We have two parameters in our line, beta 0 and beta 1. We have learned how to estimate those. We have learned how to evaluate the line. And now we have seen how to conduct inference about beta 1. And our inferential techniques are focused on the test of beta 1 being equal to or different from 0. One of the main purposes of a regression line is prediction. So we're trying to use the line to determine the value of the response given a set value for the predictor. To evaluate the line, we can use the linear correlation coefficient and the coefficient of determination. The linear correlation coefficient isn't actually a measure of the strength of the line per se, but it is the measure of linear strength. So it can be computed regardless of the line. And technically the R squared can too, because it is just the square of R. But the R squared is actually giving us information about how the line fits the data. All right, at the end of the lecture set, there's a few cumulative exercises for practice as per usual. And that brings us to the end of the material for the course. So that's awesome. So we still have the rest of today's class and then Tuesday for review. So Tuesday, we will do a very focused review session. Today, the first thing I want to do is just go over and summarize all of the inferential tests that we've seen throughout the semester. So I just need to pull up my little flow chart here. I'm just going to pause this while I'm. Okay, so this is just a very basic flow chart that I have for this particular class. This part here, we didn't cover, so I'm gonna update the chart after class. I'll take this out and I'm gonna post it. But the purpose of this chart is to try and help you determine which test to use given the situation that you are in. One of the things that students tend to struggle with is determining what kind of data they have and then which kind of hypothesis test to use. So this chart will hopefully help with that if you are kind of getting mixed up between the different approaches. So the first thing that you need to determine is what kind of data do you have and what kind and what is the question that you are trying to answer. So the first two sets of tests that we looked at were based off of means. So the very first thing, and that brings us here, right? So the first set was based off of means, which are computed using a sample of continuous values. So we have either one sample or we have two samples. If we have one sample, we might be asked a question like, is there evidence that the population mean is equal to 14? Or is there evidence that the population mean is less than 7? Something like this. So we have one mean. Once we've determined that we have one sample and we're talking about one mean, we then need to determine if sigma is known or unknown. If sigma is known, we're going to be using a z-test. If sigma is unknown, we're going to be using a t-test. So differentiating between the z and the t-test for one mean is based off of whether or not sigma is known or unknown. So that's the key differentiator between if you use the normal table or the student t table. But otherwise, the procedures are pretty much the same. Now, if we have two means, that means that we have two samples of data. And those samples can be either independent or dependent. Now, technically, if we have sigma 1 and sigma 2, we can use a Z procedure for these tests. But this is not something that we actually covered. So we didn't do this. So that means that in terms of inference, in terms of hypothesis testing and confidence intervals, we're always going to be in situations where sigma 1 and sigma 2 are unknown. Now, given that sigma 1 and sigma 2 are unknown, we know that we're going to be using a t-test, but then the question becomes, are the samples independent or dependent? If the samples are independent, we're going to use the non-pooled procedure. Okay, and if the samples are dependent, we're going to use the paired procedures. All right, so for one sample inference about the mean, we're going to differentiate between sigma being known and sigma unknown. For two sample inference about the mean, you can assume sigma 1 and sigma 2 are unknown, and then all we're doing is differentiating between independent and dependent samples. So dependent samples, as you might recall, are the paired structure. Independent samples are when you have two separate populations. So for example, on assignment number 5, we were comparing the BMI of male and female populations. Male and female populations are independent by definition, right? Whereas a paired sample is typically two measurements taken on the same observation at different time points, for example. Okay. Any questions so far? Raleigh, I'm going to post the chart after class. I'm just going to update it based off what we talk about, and then I'm going to post it. Okay, sorry, there was a question that came in direct by accident. So the question was, what is the difference between non-pooled and paired t-test? So to answer this question, I'll just bring you back to lecture set 9. Yeah. So the non-pooled and the paired t-tests are two completely different types of tests. The non-pooled procedure is shown or is summarized on slide 10 and slide 9. So with non-pooled or independent t-tests, you can see that the formulas we're using for the approaches are separating between each of the populations or each of the samples. So we're assuming independent samples So each sample has its own standard deviation and its own mean and its own sample size, and we're keeping those separate. Okay, and then there's a couple of examples of those shown on slide 12 and on slide 15. The paired t-test assumes that the data are dependent, so every observation emits two values. In this situation, we're actually going to work with the differences between the values. And as a result, our interval and our hypothesis test are effectively one sample procedures that work with the differences directly. And there's examples of those given on slide 25 and slide 28 of lecture set number 9. Okay, so independent samples use the non-pooled procedure because they're two separate populations that aren't related. Paired data is typically, or dependent data is typically paired. So every observation contributes two measurements, which you then have to find the differences of and basically run a one sample test on. And then if you need further examples are given on assignment number 5. So on assignment number 5, question 2 was an independent test. Question 3 was a paired test. Okay, we also talked about the ANOVA procedure in lecture set 11. This is how we test for a difference among 3 or more means. So the ANOVA is basically a generalization of the 2 sample test. So we're moving from 2 to 3 or more samples, and we use the ANOVA in that situation where we have 3 or more samples. Okay. Now, we also talked about 3 other types of hypothesis tests. 2 of them were chi-square tests. Okay. And one of them, one set was the regression inference that we had just talked about. Now, for the 2 chi-square tests, the easiest way to determine if the tests are different is based off of the structure of the data. So for the goodness of fit test, we're going to have a frequency distribution. So for the goodness of fit test, we're typically going to have some number of outcomes, and then we're going to have counts for each of the outcomes. For example, on assignment, well, I don't remember exactly what assignment 5 was, but in the lecture notes, we were testing to see if the color distribution of M&Ms matched what was stated by the company. So there were 6 different outcomes, which were the colors of the M&Ms. And then for each color, we had a count of how many of the M&Ms in our sample were that color. So that would be a frequency distribution. And that's where we would be applying the goodness of fit chi-square test. The independence test is utilized when you have a contingency table. So basically when you have 2 qualitative variables and you have counts for both structured in a contingency table, that's when we would use a chi-square independence test. So differentiating between those is basically a question of how many qualitative variables do we have? If I have 1 qualitative variable, it's a goodness of fit test. If I have 2 qualitative variables and a contingency table, it would be an independence test. And then for the regression data, this would be based off of an example like what we just saw. So if I have a paired data set, but the variables for each observation are different, and I wanted to predict one from the other, this is regression, and then I would be using inference about beta 1, like we just saw at the end of lecture set 12. Right. So I'm going to clean up the chart a little bit based off of what we actually covered, and I'm going to make a few little changes just so that it's a little more direct in terms of following it through. but hopefully this resource, once cleaned up and reviewed, will be helpful in determining the different types of tests or the type of test you need to use based off the problem you're working with. Okay, so any questions? Yeah, I think they're already there. Okay, so on, I haven't posted them yet, but I'm gonna put up the same as I did for the midterm. I'll put up practice problems and I'll put up some sample finals. I think I have a couple. So those will be posted in the final exam folder. And I'll also post, and I will also post the flow chart once I have that cleaned up. On, let's see what day it was. I think it was, today's Thursday. So this would have probably been on Tuesday. Yeah, on Tuesday at 7, Kathleen or Dr. Laura Lowry Batty posted an announcement on the lab merge page. So this would have come to all of you. The title is Wonderful Opportunity for Stat Review. So there's a free final exam review for Stat 151 that's being held via Zoom on December 6th from 5 to 8:30 p.m. So you can sign up using the Google form that's given in this announcement. And from what I understand, the cap is around 300 students. So it's a first come, first serve form. So if you're interested in attending this review, that link is on the lab merge page under announcements. Okay, December 7th, sorry. And that link is on the lab merge page under announcements, and then you have to sign up online for that review. Okay. All right, so on Tuesday, I'll work through some practice problems with you guys to get ready for the final. And if anyone has any questions, Meg, I have no idea if it will be recorded. My guess would probably be no, but I don't know. You can email the organizer and ask them, and they'll let you know. Right, so on Tuesday, we'll do some formal review. If anyone has anything in particular that they would like to see before or on Tuesday, please let me know. The reviews are always a little bit more interesting. Sorry, Danielle, are you saying yes, it's going to be recorded? Oh, right. Totally losing my train of thought. Sorry. Just obsessed with that USB stick. Oh yeah, so if the reviews are always a little more interesting, or a little, at least they feel a little bit more helpful if students have questions that they want to see in particular. Otherwise, I'm just going to randomly jump from section to section and kind of pick problems apart as I have them set up. For the rest of the time today, I was thinking I was just going to let you guys go a little bit early for once, and then we can kind of run into the weekend with, or I was going to let you guys go a bit early, but I'm going to hang around until the end of class. So if anyone wants to ask questions about assignment number 6, I'm going to kick around for that, or general review questions, that's fine too. But otherwise, I'll let you guys go if you want to go, and I will talk to you on Tuesday.